Yeah, thanks very much for the opportunity, or rather the challenge that was posed by Philippe to present something about illustrating maths. So it will be quite experimental. So it's the first time that I try this. The idea is that we also get a bit active, like I think you have been just now with GP. So let's go into it. And it's about, as in the abstract, I'm regurgitating the abstract here. So only check the bold-faced words maybe as the main parts. So symmetric spaces are part of COGENT, and the relations to arithmetic, and that's what is underlying that process here. And it's illustrated in the form of the hyperbolic free space, and the main thing that you need to understand is the orbit space of a certain discrete group acting on hyperbolic space. So what we get there is a fundamental domain. I think it has been already part of what people have been talking about the other days. So that's the main object that we are looking into. And so first I give a bit of background, and eventually we'll arrive at a new kind of polyhedra, and then we'll go to the 3D printing thing where you should hopefully get active. And we might get a chance to get this directly printed on the fly if it works out. So we're setting up a Zoom link with a Fab Lab over there. Let's hope this works out. It's all a big experiment, as I said. Okay, so let's start with the very basics, a tessellation of the plane. Okay, we have things like tiles with no overlaps, except possibly where they meet, and of course with no gaps. So it's really a tiling of the whole thing, like in your bathroom. The tiles should be neatly glued together. So on the left, you can see that there is a single type. On the right, we have the same type but two sizes. So it's even a regular tessellation, so that's one of the maybe easiest ones. And so a bit more pertinent to most of the cases that I'll be talking about will be those types of tessellation where you have several building blocks. So on the left we have two, on the right we have four different types of building blocks. Okay, now you may have seen the connection to illustrating maths and artworks is that tilings can be found, for instance, on the left here in the architecture world, and also carpentry on the right. Then famously, you may have seen Escher's work, part of it. On the left we have the flying fish. On the right we have specific tiles, the so-called rep tiles. So he was even playing with the words, and so I've taken the liberty of also talking about crocodilings and dovetailings. So for the Angry Birds fans on the right, and for the for crocodile fans, I don't know. Okay, now the point of the whole thing is three-dimensional tessellations. So what do you know about tessellations of free space? So the easy case, I'm sure everyone knows, is you take a cube and stack cubes of the same size, or even like rectangular objects of the same type will also tile nicely. But then there's one more, which you may have heard yesterday. You're not allowed to speak. A three-dimensional tiling of this Euclidean space in terms of one type of building block. Do you remember when? Yeah. No.
I wrote it down because it sounded so cool.
Yeah. So, and not so many actually are known. And so here on the left we have the one that Graham was talking about yesterday, and on the right there's another one. So it's slightly less regular. But on the left here is maybe a bit more proof of the fact that they are really tiling. Yesterday it was kind of going all the way as a curve, and here we can really see them packed. Okay, so, but this is Euclidean space. So let's take hyperbolic tessellations. Like claim, there's much more freedom, and we'll find new kinds of objects there. Okay, and for that reason, I try to recap a little bit about the hyperbolic plane, and then we move to the hyperbolic space. The same intuition kind of works. Think of the hyperbolic plane as sort of different sections in a three-dimensional setting. So hyperbolic plane, we have the Poincaré disk model. Take the interior of a disk, and there we have sort of geodesics, so the shortest lines, which are segments of circles, and they are orthogonal to the circle that bounds the disk. And as a special case, we have the diameter of the disk. Then there's the upper sheet of a hyperboloid in R3. And so given by, say, the equations in R3, well, by this equation, 3, and only with the upper part, so where z is greater than 0. That's another version of this. And the straight lines now are given if you take a plane through the origin and intersect that hyperboloid. That will carve out a conic, and that will be sort of representative of such a geodesic. And we can actually compare the two models. So I tried this. Maybe it's a bit weird looking. No, actually, I think I copied it from somewhere. But you get the gist. So the hyperboloid up there is being projected down to the Poincaré disk model in green. You can see the hyperbolic line and the P for Poincaré, P line as the projection of the red line down there. And it's a bit more zoomed in here on the right. So that's how you should think of those lines, shortest geodesics. And we could actually instead project not from, here we project from the point -1, you can see here, to the plane, or rather disk, the unit disk in the XY plane. We can do, we can actually project from 0, but then project onto something a bit higher, and that's what's done here. And that will produce the Klein model, Klein disk model again. And this time, here you can even see the K line, or Klein, as the projection of the hyperbolic line, but then it's straight in the usual sense. So it loses kind of information by dropping the angle, but essentially one can get it back. So it's a lack of conformal symmetry. And the final one, and that's maybe in a sense the most pertinent one for this talk, is the upper half plane. So yeah, you just take the usual upper half plane and the points in the plane above the real line. The shortest ones, the geodesics in this model, are the ones which are straight orthogonal to the real line and half circles. Now, tessellations of the hyperbolic plane in the Klein model, for instance, look like the one on, look like this one. Poincaré, it's slightly curved and more curved to the outside on the left. So that's by heptagons. And so there's already a nice variety of such tessellations in the hyperbolic plane. And if we draw that in the upper half plane model, then it looks roughly like that. So you can see how things get seemingly distorted, but it's all about thinking what the shortest lines are. Okay, now from two dimensions, just as an aside, in Durham, in the maths building, there is something like the hyperbolic plane. So a very rough approximation, as you can see, only 2 iterations of that process. And the more correct, somewhat more correct approximation is given here. So that's a tessellation of the hyperbolic disk in the Poincaré sense. Okay, now let's go for hyperbolic free space. And here is something that I would like you to try and visualize. So on the left, you can see the convex hull of 5 points at the boundary. So these lie on the bounding hyperplane in the same way as you have the real line for the hyperbolic plane. You now have a plane, a complex plane, as the boundary of your upper half space model. And then the geodesics are still half circles that are orthogonal to that bounding hyperplane, and the ones which are going straight up to infinity. So, so here we have 6 points, and we take the convex hull of 6 points, the hyperbolic convex hull. And if we watch from the point at infinity, what we see is the picture on the right. Does that make sense, kind of? Right, so this line, for instance, corresponds to this, this half circle. And then those ones correspond to the bigger circles, and the point here corresponds to the line going up to infinity. Now, a bit more challenging is maybe, and this arises from the action of a discrete subgroup, and the discrete subgroup is related to Zi. So the Gaussian integers, a plus b times I, where a and b are integers. So the group of matrices, 2 by 2 matrices with entries in that ring, will give you a nice action on hyperbolic space. And the fundamental domain of this, so an orbit space, where every orbit has one representative, is given roughly in terms of this bit, well, up to some finite indexing problem, which I'm not going to address. Okay, so let's take the next case for z root minus 2. It looks more interesting, so it's harder to envisage, especially if you look at the left picture. Somewhat easier to see on the right if you only look from above, again from infinity. Then the picture, so the plan looks kind of more convincing or more straightforward. Here x is root minus 2. Yeah, it's up there. So this is how we can try to visualize the whole thing. So here we try to put half spheres which bound that fundamental domain. So on the left, this is essentially the same picture as the other one, but now with half spheres thrown in. So everything above those half spheres is kind of part of the fundamental domain. And if we watch from below, it will look like the one on the right. And that's very close to that plan, so the previous picture on the right that we've seen, so like this one. So that should be reflected pretty much in that. Okay, now if we turn this picture slightly, so the right-hand one here, and push the point at infinity to a finite point, and take the convex hull, then we see kind of the polyhedron appear, at least in a combinatorial sense. Now, straightening out those half circles into lines will give us a picture, one on the right. So that's those should not really be there. Oh, that's stupid. Yeah. So you see a number of rectangles, a number of triangles, and that's supposed to be the object that corresponds combinatorially to the left. So now the claim is that either of these two polytopes, the first one was an octahedron, right? We had 6 points and the convex hull of those. That was for Zi, and this one is a cube octahedron. At least it's supposed to be, if done right. And then we have a tessellation hyperbolic space into one type of polyhedron, just like we saw in our first tiling picture. And both, of course, come from number theory. So now, instead of having I, which is root -1 and root -2, we have a scaling parameter d, which plays the role of 1 and 2 in those cases. So for each d, in principle, we can find polytopes, and very often rather beautiful and I think new ones. And a student of mine, Josh Inoue, a couple of years back, found a way to make them more symmetric in a very concrete way, and that gave rise to jewelry and other decorative objects. So the pictures that came up, so some of those, for instance, for d equals 3,606 on the left, gave you a rather nice symmetric polytope, and a similar one for 226 on the right that already showed that something nice was going on. And so we produced quite a few more of those. And then there are wireframe models of those. The one on the right looks very much like the previous one, I think, even with the right of the camera. And I think I tried to get the same thing in place on the left. So let's just compare. It's pretty much, yeah, I think, well, if you allow for some slack. So on the left, this is bronze steel, and on the right, this is gold steel. So these have been produced by Shapeways, so a 3D printing company, right here, to be recommended. Oops, and yeah, so other interesting materials like precious metals. On the left, we have silver, and on the right, that is plated gold, plated rose gold, to be more precise. So I call the left model flatter Earth, because its shape really does remind me a bit of the Earth, and it does flatter the Earth. And on the right, the delicacy is rose gold plated. So others you can see more complicated looking, and they are for 2,409 on the left, and on the right there is 209. And there it's no longer wireframe, but I produced a few of those faces, still leaving out quite a few to make it transparent, or at least kind of see-through. And I think it has a certain appeal. And in fact, Alexander liked it so much that he purchased it yesterday. Okay. Well.
He gets the commission.
Ah! Okay, and you may or may not have seen it yet. There in the bibliothèque, there is a little exhibition that we put up yesterday evening or afternoon, And so it will be there today and tomorrow for sure, and possibly a few will be left afterwards. That was kind of motivational for what's coming next. So now I want to go on to the part where we go from model to the design, to the 3D print. So first from an idea that you have to a model. So that will be the part where I ask you to participate and throw in ideas and try to experiment. So the program, the software that I'm using, I found very useful. It's OpenSCAD. Especially if you want to design in a parametric way. So meaning that just one or two changes will allow you to have a whole family of objects, depending on your specialization. And that makes it very, very useful, especially for objects that you define like in a mathematical way. Others are Fusion 360 for those interests, and Rhinoceros is also something people have used, and I've tried to use it. It's a bit more advanced, and typically takes a longer time to get something out of it, and it's not too expensive for students and educators, like I think 150 or 200 pounds maybe. Euros, and yeah, for experts there are even more complicated such programs. Then from the design, once you have a design, and we'll go into that, you produce a universal printable file. So that means independent of the printer that you're using. That is something in OpenSCAD, you simply have an option, export to STL. That's a thing to remember. STL is, I think, the standard format, despite having possibly better ones around, but this has been around for decades, I think now, and has proved to be rather robust. So it's recognized by almost any printer. Once you take the next step, which is, similar options for the other programs, of course. So the export to STL, I mean. Yeah, the problem is, of course, that if you design, very often things will not work out as you imagine. So it looks fine, then you ask the printer to do it, and nothing works. So that's the beginner's luck. So from STL, finally, you need to get it to the printer. And there, it's really dependent on the printer, and there are so-called slicer programs. What you do is you take the layers of your object, so you cut your object into horizontal layers. And then the printer head will go precisely to those places where the computer tells you, leave a blob. And sliced into horizontal layers and encoding in a so-called G-code file. You don't need the bottom here anyway. And you also need to adjust certain things. Well, maybe I can. Okay. So the speed of the printer head, the temperature of this nozzle, which gets very hot up to typically 210 degrees Celsius, and the type of material. Typically we take PLA, that's a standard thing also for the Fab Lab over there. They use a specific type of printer, which is very, very solid. It's called the Ultimaker. They have four Ultimakers over there. And one needs to adjust material, support material in particular, because you don't want your machine to draw in midair, because it will simply drop down to the build plate. They try to make sure that, that there's enough support, and often you just need it at an angle. Up to 45 degrees is usually fine. Sometimes even 60 degrees overhead will work. But if it's more than that, then typically you should definitely ask the slicer program to produce what's called the support material. Yeah, so here PLA is in boldface because that's the most standard and the most reliable one, which doesn't clog your printer.
Is there a theorem to the effect that the one skeleton of a 3D polytope is printable?
I don't, so depending on the angle?
Yeah, but that you can always choose.
I think that's also dependent on the material, because it might catch a glimpse of what's there, depending on how big it is, right, and might still cling on. And if it's too small, it will just drop down. So I don't think mathematically you can quantify it. But so it's a typical experimental thing or experience thing. So you do your 10 prints, and you figure out 5 of them were complete rubbish. 2 of them were maybe not so great, but maybe the last 3 kind of worked. And what I didn't do is to write down all the data, which you should, when things work out. Yeah, so I've wasted lots and lots of time.
How many printers that work with those nozzles? You just have powder that you center, titanium or something?
Yes, so the ones that typically you have in your home are just these plastic printers and PLA. The ones that I produced here with those bits, they are powder printers, so gypsum maybe, or silver, even silver powder, I think. And then the laser comes and glues it together very, very precisely. And then the next layer, very thin layer of that material comes across, and the laser comes again. In the end, so you're seemingly wasting a lot of that silver material. Imagine, right? You have silver powder and just that tiny little thing. So what do? You suck it back. So you take a vacuum, essentially a vacuum. Yeah, so it's quite amazing how they do it. That was the more expensive machines would do that. So we don't have those in the Fab Lab, so we cannot show this. Yeah, so I think I said something like 3+ stages. Typically the post-production, and that takes quite a long time because something goes wrong and you check whatever went wrong, like thin connections or it broke, and then the support material takes forever to build up. The problem is you need to find a sort of golden path between all those requirements. If you give it too much support material, it takes forever. A print typically, like of this size, will last several hours. So if you take a ball of the size a few centimeters, you likely are waiting for several hours. You don't really want that if possible. So you try to find arrangements. But in a first, and then you correct your errors. Let's just. There are programs that help you. Often your file becomes huge, bloated, like 100 megabyte or 200 megabytes even. And then you can find programs like Mesh Mixer, who will allow you to cut down on the size. So your triangulation is far too specific, far too detailed. So you take a smaller, a less stringent one, less precise one, and that cuts down the size often by a factor of 2 or even 4, and then very often you can do it. So for instance, Shapeways will not accept anything above, I think, 70 MB. So you have to cut down your object into right size. Okay, yeah, Mesh Mixer. So here's an example how it looks like in the program that we are going to start in a minute. Yeah, so you can see that this has been drawn. It's the same object as we've seen before for 3606. It's even in the file name. And on the left, there's part of the script that produces this. So now the great challenge for you. Write a quick script in OpenSCAD. And so I'll go through a few of the most basic commands. And it's surprisingly fast that you should be able to produce something. A printable STL file. Okay, quick introduction. So let me try to skip this one. I think that's too small. Like that. Okay, just to get an idea, here we have an overall constant that I call my Fn. So Fn I take as a placeholder for fineness. So my fineness is 20. If you make that too big, it will take forever for the program to render. So that's another thing to keep in mind. Save your time. Okay, so the first stupid thing to do is let's draw. So I think function key and F5 will give you a chance to display the whole thing. Simply there. So take a cube. You draw a cube by simply writing cube and you give it the dimension. Well, if it's cube, then you implicitly assume they all are the same edge length. So cube 5 is this. Fine. And so we can try more.
That's a solid cube.
That's a solid cube. That's right. Okay. And now here we have a variant where you can specify the 3 different sides, and you will see that it will look as you expect. Okay. In the same way, we can go to a sphere. I call it 6. Now, it doesn't look very spherical if you look at it. So you can see that the fineness, actually, fineness parameter, let me try just for once, 120. And let's see what, oops. Sorry, I have to, no, I didn't specify the thing. It has a default, so I need to tell it $fn equals something. And I have this constant in front. So let's look at it with 20. Oh. Okay. 120 looks better. So, but as I say, for later on, you will not want to do that at an experimental stage. Try to keep your fineness low for that time. Okay, other things to experiment.
Does this make a difference when you pass to the other thing, the slicer? If you have a
Yes.
slicer
Yes. Yes, it will respect this triangulation. I mean, what you will get once you export it to STL, it will remember those pretty much as faces. So it's pretty bad as such. So you really want to do that, but only do it at the very final step before the export to STL. Otherwise, you waste lots of time.
It won't make any difference with the slicer, no, in the end, minus.
Maybe I missed. The slicer takes whatever it gets, but
yeah, but if it's very fine with tons of triangles, the slicer will take a little bit longer. But since the printing anyhow is slow, that doesn't matter.
No, but the point where it's slow, the thing that's slow is the rendering process in OpenSCAD. That's what I meant. Yeah, sorry. For the slicer doesn't really care. Yeah, that's very quick. It just approximates anyway. It will ignore any too fine detail. Yeah, sorry. Yes. Okay, so the sphere, then we have cylinders, then we take, now it gets interesting, let's take differences. So Boolean operators where we take intersection, differences or union of objects. That's one of the most powerful functions. So we take a cube minus a cylinder. Where's the cylinder? So I've taken away the cylinder here. So the cylinder tells us it's radius 4, height 2. And just to make it look a bit more cylindrical, I took the 20. But you can see this flickering thing here. That's when you are too precise, and this may also cause a problem if you want to export it. So instead, let's take away a little bit more. So what we do is we have the translate function. We just translate a thickened part. Well, actually, I just took the same cylinder, just slightly over the origin, and then we can on it. Let's take the whole thing. Then Command Shift D will remove the command. Will remove the comment things, and we can see this flick disappears. So that's, I think, an important part. Then we can look at spheres and take away an internal sphere. Wrong way around. So this one, let's try. Okay. Minus another sphere inside. Well, we can't really see it, but if we take away hollow, sorry, I'm going to make it larger. So that's, so the first sphere was of size 0.5, 2.5, and then I took away a sphere of slightly smaller size. It's all automatically centered at the origin unless you tell it where it's supposed to be. And then we take away the cube, like so the first quadrant will be just cut out because the cube size is large enough. So then that's another possibility. Okay. And we take of a cylinder. Maybe I can skip that. So you can use modules like functions. They might not behave exactly as you expect, so it takes a bit hollow sphere that uses a previous rotation of a cylinder directions. And so we'll take a sphere and cut out a cylinder in all three spatial directions. So you should expect a sphere with 6 holes. So let's take the hollow sphere here. That's too big. Yeah, here we are. So you can see all those are being taken away, and you really use that sub-function sort of inside that function. So that works as you might expect in such programming topics. Here you may want to use for the experiments to come, in the sense that we produce hulls of objects. Like take a sphere, take another sphere, and want to take maybe the line between them, the edge connecting them. So like in those wireframe models, that's often what I'm doing. Okay, so we have the points, so the vertices of a cube, just written out as in terms of -1s and +1s, or 8 possibilities. And then here I take a random set of edges, call them my edges, and then the full set of edges I call cube edges. So let's have a look at and then there's a Minkowski hull. So the hull means it's a convex hull of objects. And then Minkowski makes it as a more complicated object, but still sort of convex hull. So if I now ask for, say, the first edge, that's called, my edges 2 is called 1, 3. Right? As in Python, the lists always start with index 0. So 1, 3 is, now if I take this away, and then this is sort of the hull between two vertices of the cube. So this one is like 1, 1, 1, I guess, and this is maybe -1, -1. And well, whatever. So I need to. So here you can see on the left lower corner, you can see the X, Y, and Z axes. That's often helpful. Okay, so that's one thing. Then we take several of them. So here you get a more complicated picture. These were the random edges that I drew between those 8 points. And then the more structured version, let me do that as well, but in red at the same time. So it will now look like, oops, so I've translated a bit to not have it same picture. But it's rather straightforward, I think, in terms of understanding what this does. And the final suggestion, because it's very powerful, there's something called, I already showed the picture. So, okay, here is a function called linear extrude. And so you give it height, a twist, and the number of slices. Well, let's just, for a change, to see what, there is not much changing. Let's take another twist by 90. And you can see that this object is being produced. You take a square, and you subtract a square of smaller size. Let's make it maybe a bit, can even go up to 20, and it looks a bit nicer. The offset here, being r equals 10 for the first and I equals 8 for the subtracted one, will make sure that there's still something there. And so you just take that frame and rotate it around going up. So linear extrude is a very powerful command. So, so maybe like this. So those are the ones that I would throw at you for inspiration. And then it's essentially stacked, yes. So the number of slices here, 50. If we increase it, you can see it's much smoother, or it's supposed to be much smoother.
The other things you showed me, there's this thing that when you say you get problems because it's not manifold, it's less than 1
Yeah, that's the next problem. That's the correction bit that I skipped. So it's, for me, the best program that changed that, or that helped with that, was the NetFab. And it used to be free, and I think now it's not free, and it's amazingly expensive, like £1,000 for, it's a bit crazy. I still have an old version on an old computer, that's still okay. So but Mesh Mixer does it, and Mesh Lab. Mesh Lab is pretty decent, and Blender as well. But Blender is very complicated. You can make lots of mistakes, and you go anywhere, and you don't know what you did. But if you understand Blender, this is, I think, a wonderful tool if you have the time. And this will definitely throw away. Nowadays, slicer programs have become much better, and they also detect errors and correct them. I've used them like for the Flash print, it's Flash Forge special machine, and the Prusa slicer. So one of the more famous slicers these days is the Prusa slicer because it's trying to be more universal. And I've corrected already a couple of files in the Prusa slicer too. So that I definitely would recommend using. I think it's even compatible, hopefully, with the Ultimaker. Maybe not yet, but it will eventually be. So they are trying to be very inclusive. Okay.
And questions of projection solved automatically. If I wanted to print stalactites, and the difficulty, but I might spot that
yes.
it was stalagmites.
The angle.
Is that done automatically by the printer, or you have to do
No,
it?
you do that. I mean, there are ways, depending again on the slicer program, where you can do it rather easily. You can fix, for instance, a face and tell it, okay, put that face as the ground face. And that's very helpful, because you want to try different things out. And then you ask it to produce support material, and it gives you a suggestion. You can override it, but it may actually take quite a while to get it right. So it's a lot of experimenting indeed. So for now, I would suggest just to throw anything at it, and then we could hopefully send it over to the Fab Lab and have it printed. So maybe we can connect to them right now. Are they online? And could you ask him to check whether the camera is already?
To install something.
Oh yes, OpenSCAD.
Oh, all right. Okay.
Ah, I meant. I emphasize. Yep. Yeah. Please download OpenSCAD. It's pretty straightforward. OpenSCAD.org. And I think the instructions how to install it for Linux, Windows, and Mac are very straightforward, very easy. And you'll probably get a new version, a better version than I have. Hopefully it's compatible. Do you have it? 21, okay. You see how old-fashioned I am. Okay, and just motivate you more. So here's something that I tried to produce over the weekend. Unfortunately, it had to travel. So it's chocolate printed, 3D printed chocolate. Do we have a plate by any chance? No? Okay. Maybe. No? Okay. Oh, pity.
Do you want a very nice plate?
No, just plastic. Anything just so that I don't need to touch it myself. Disconnect this one. So I just pull it out, right? Or is there anything? Ah, fantastic. Yes, it's great.
Partage la vidéo en fait.
Ah, la vidéo possible.
Ouais.
Alors, si je lui nomme animateur, normalement c'est bon.
Oui. Ouais.
Oh no. Okay, well, travel. It didn't work. Well, yeah, no. Well, he's.
Yeah, but it was rich chocolate?
Yeah, it's chocolate. You can eat it. It's good.
Really?
Yes.
That's incredible. It's too bad, but at least
Here I can see
we
Paris still,
yes.
right? So that's, and maybe here France. Oh no, that is Sydney. Ah, here's a skull. No, nothing works. Okay.
It's not.
Yeah, and anyway. Sorry,
So at least you can read Paris there. And eatable.
Yeah, it's eatable. It's fine. It's actually quite decent taste. But yeah, through the trial, everything was crushed, I'm afraid. Here you can see still Sydney, kind of, the opera. That's, and here you can see Paris, but...
I thought we were supposed to eat it. No, we looked at it.
Yeah, it really, first to look at it, and then just take it away, because it's so embarrassing.
And you can eat Paris if you want.
Yes. So see the Ultimaker, great. So you can see the printer head go back and forth or sideways, and it will put one layer on top of each other. So if you manage to get something within the next 20 or 30 minutes, we can try to print it live. Imagine that. You create. You feel like, it's almost feeling like God. Something, something emerges. Okay, sorry. Sorry, I'm overdoing it, but I think I'm fine.
I think Convex is 3D printing.
A much better one, I'm sure. So what we need to have is a 3D printer where you have like laser printers coming together, and only at the points where they meet, there will be a sort of one blob that's being created. And then you should have it on three sides, sort of, that it just take one picture. It's like an Insta 3D, bang, and then it takes it out of the liquid. That's my dream. And I think in miniature, they already realized that. So
So in fact, what you are dreaming is Star Trek replicator?
it's probably better than Star Trek Replicator. I don't know exactly what they did, but it sounds like... How long did it take for them, for the replicator? Like a minute?
You mean in the series, it is instantaneous.
It is, okay. Yeah, then precisely. Okay.
So you are telling everyone that you have never seen the show.
Yes, I'm not a nerd. Not enough of a nerd. So I've lost any respect that they had before. I don't know Star Wars. I don't know the What? You didn't know? And you could...
Can you tell us what is going to be printed?
So which one is that? So I've sent him a few. What could that be? So it's not one of the...
You want to know which file it's printing?
Yes, please.
It's soap.
Soap dish, I see.
Take it from Star Wars.
It's quite small, but yeah, I didn't change the size that you send it, so yeah, it's quite small, but yes.
But then it's fast. And did you...
It's 2.5 hours, and I launch it at 11.
Oh God. Okay, so it takes... So did you try it with the support material?
Yeah, it's with soluble...
With soluble, great. So this is a very special one because it needed a lot of support in principle. And you can have support that typically you have to break it off and make sure that things are still alive afterwards. But the new machine with the Ultimaker 3 allows you to have soluble material. So you throw it in water overnight and then it dissolves. Sometimes it dissolves a bit earlier, but and hopefully it's much better than if you did those standard supports. Cheating? You can also download STL files, right? Well, but at least you have to modify them. So you cannot just print something that you've taken from. But it's good. You can include STL files. I should have said that, indeed. And then adapt something, cut them, or make something mathematical out of it. Yeah. So there's Thingiverse is one of the sources where you find lots and lots of models. And then you can take that as your basis and adapt. I don't know the copyright. Oh, what is going on? Oh, so I think he's adjusting the camera.
Small keyring, p-keyring.
Ah, okay. Oh, that's being printed now? Okay. So a student of mine once made a small pi keyring. So a keyring in the form of a pi. So a curly or a curved pi. And it has a ring on top. So you can just put it in your kit. And so this is being printed right now. So you can see how the first layer, yeah, now it's, okay. And this should actually see the pi. You can roughly, it's sort of a whitish. So what's the material? PLA, I suppose?
PLA, yeah.
And is it transparent?
Yeah.
Okay, great. That's cool. And so here you really feel, you see it appear from nothing. It's very satisfying.
What will be the strength of this?
It will just be very, very short. So like maybe half a centimeter high.
Yeah, but for a keyring, I mean, can we use...
Oh, the strength as material. It depends a bit on the PLA that they're using. A better material, but more difficult to print, is PETG. So, and others, you've seen my keyring. So I have a keyring made out of HP plastic. So that's Hewlett Packard. And that's quite flexible. Yeah. So that's much better. But this will probably be strong enough to keep in. Ah, so it's done. That was fast. Are you sure this is all? Okay, great. Yeah. So finished model. So can you produce something of that? Yeah, the hole is supposed to be there. It's a key ring. Yeah. But now you have to take it off, and it's a glass plate that it cools down. So they're much better built plates nowadays, that from steel, but which can bend, and it's so helpful. you can't imagine what people have suffered through with that material, with that machine. Even over there in the Fab Lab, he told me they need to scratch things off the surface, and they have destroyed. No, you can use the blue tape especially, right? But it's not always the best choice. I know. But it can help, yeah. Why not? Imagine, I think it's a standard thing for people working in DIY. Okay. Okay, good. Germain, do you ever use blue tape?
I have some, but I don't really use it actually.
Because it doesn't help so much, right? Or in the end?
I think maybe for material ABS or something like that, but for PLA, the naked glass is better. But yeah, for maybe for the one we do not have a heating plate is better. But for Yeah, for PLA, I think it's for me. I find it better to use just the glass.
Okay. Ah, so it's now changed. It has just changed from.
Yeah, this is how we change
support material.
So we can change the material.
Right.
Yeah, he has one nozzle which can be going up and down depending on if it's needed to print or not.
Oh,
so
okay.
The two nozzles are not at the same level every time, so it's better. Long time, some years ago we have another one which has two nozzles also, but the two nozzles have to be put really perfectly at the same level, which is almost impossible, and
right.
don't have a good rendering. So these techniques with a mobile nozzle, it's really good.
Okay.
If you want,
Great.
see.
Ah, you can see it from the top. Yes, that's nice.
This is the shape of the
printer head.
support. Yeah, the support.
Ah.
The
oh, I see.
triangle is the shape of the support.
Okay, okay. It's now it's better. Yes. Right. So it's hexagonal kind of support, right?
Yeah.
It looks like snowflakes almost. Okay, great. So, any first?
I can't install.
It's you can't install. Oh,
No, it's
what?
oh, no. Something with my Debian. It doesn't. Yeah,
Oh, but you. You got this one.
No, I tried the both things, but
Yeah?
I'm trying to fix anything, whatever.
Ah.
Small file.
Yay, yay.
Boy.
And do you have other colors? I mean, transparent is nice, but maybe. Or am I being too demanding?
Yeah, maybe I can send one of the.
What, red?
The printing I have to check.
Red or blue, if you have one already lined up.
You want what color?
Red or blue, either one, just a bit more visible, especially for the path that the print head.
I will see what I have.
Or black, or what are your favorite? What are your colors? Did you get anything out? Not yet. Anyone? SCL? Did you download some?
I downloaded something, but I don't know how to modify it.
Yeah, let's see. Oh, yeah, that's very hard to print because you have to make those very thick.
I can imagine that's very difficult.
Do you have the parameter to change the thickness of the line? Maybe
yes,
TH looks like thickness, maybe? It says 0, but obviously that's maybe not.
Oh, I mean, in the arms, right? I don't know.
Okay, let's have a look. I don't know whether I can understand. Maybe this NR times ring minus 1. Can you just add, or times 2? Take it 2 times here, or 3 times, to see whether, if you then know the whole thing, 2 times the bracket. Yeah, and then just rerun it.
Yeah, it's gonna take a very long time.
Ah,
It took
sorry.
a very long time.
So that's probably due to it's being too fine. That's what. Sorry. You should have warned me. I didn't realize.
Quick one and the fancier one.
No, well, really? There's F5 and there's F6.
You have preview and render.
Yeah, the preview is yeah,
And
that's right.
preview is
Preview
not
is
that
F5.
great.
That's right. That's a faster one.
Yes,
Yeah,
that's
you
the
shouldn't.
faster
You try not to touch the F6. But, oh, it's okay. But it's just shorter. Okay, but it's good to know. So then that's how you figure out. Oh, there was already times 30. So we could have guessed that this is maybe okay.
Ah non, c'est pour ça, tu dois mettre tu dois mettre des parenthèses à la fin de juste avant le crochet, tu mets des parenthèses.
Ah, could you set the finest parameter next time, right? From 40 down to 20. It should be so much faster, I think, because it multiplies at times, which is really stupid. But okay, great. Yes, yes, nice. Are you trying?
So I'm away that you did.
It doesn't matter.
That's because it's easy to do, because you have to cube it, you subtract.
Right, right.
So the goal is to find the exact...
The formula.
Yeah, they don't give the formula. They don't give the STL file.
Well, but if it has a name, if you just Google STL and this thing, you might actually find someone who already... Pink. Oh, that's good. That's good. Yeah. No, red or pink is a nice color. Great. Thank you. Yeah, it glows even from here, so that's great. In the front.
I want this one.
Ah.
I need a keyring.
Ah, perfect. But, well, you should have your. What's your favorite number?
Number?
Or a favorite mathematical? Yeah, maybe transcendental, like E or pi or gamma, or produce that number and with a hole, and then you can use that as a keyring, and then it's your own. This one is you just take it from somewhere, but it's so much more satisfying.
Yeah. No, you're right.
It's really a great thing.
Can have a keyring K80
That's yeah, exactly. Try to write it. There are examples that you can pull. Ah, sorry. Still doesn't. Did it work? Did it work?
It didn't. No, I mean, I'll have to start fiddling with my Debian, and I.
But well, why don't you take this one instead? Well, it's a Mac, but I don't know whether you can. Yeah, just.
All right, okay,
I think you can play around with this one, or just have a new one.
Yeah, just to fiddle, just to see how it.
Yeah, exactly. You need to get used to it. Okay, let's. You really need to press it somewhere in the middle.
Right,
more in the middle. I think more in the middle.
Okay, yeah.
Maybe if you want a new one, just and then you can copy paste back and forth.
So can I destroy this one of yours?
Yeah, of course.
Okay.
This is,
So I just try a few things to see what.
I don't know why, it's just a weird little shape.
Where's the run command?
anything?
Nothing yet.
Nothing yet. But did you try to download something and play around with that?
I had something in mind, but I didn't download anything. I just, I'm not really familiar with that. Could you make like a path from point and like thicken that? Okay.
But paths are actually delicate to print.
Just
Nice. So you really have to thicken it quite a bit. otherwise will just easily break or will not even print. If you, for instance, want to have a spiral up like the guy over there, it's very hard. So you need a lot of material to make sure that it doesn't fall down, and then it's very delicate. And most likely, when you take away the support material, it will be destroyed. So it's such a so try to think of something more thicker. So, like a graph? You're thinking of
a fat knot.
Yeah, let's take a fat knot. Yes.
Like a big, one of these weird embedded foil things.
Yes. And just take a tube around it.
Yeah, I was just going to do that.
Yeah.
Like a piecewise.
But you wanted in the but his program should do that, right?
Yeah, I mean.
Well, maybe you can liaise. And
Do you think you've got could you develop a good working relationship?
Perhaps.
Yeah. It's going to do another?
Oh, there's something in chat.
Oh, in chat? Oh.
That's what I should be keeping an eye on.
Maybe. Yeah, I think maybe you've got the wrong button here. If you want to always participate.
No, you mean this? But I only have these buttons.
No. In the chat box here, I think all panelists and attendees maybe.
Or
I think there's nothing there anyway. So
Benjamin, what's next?
Next one is
The associahedron?
yeah.
Yes. So we get an associahedron.
Oh, I was going to ask for one of those.
Well, you will have ones as jewelry over there, which are in the box. So you know that in the library you have the exhibition, so whenever you find time, drop by. And if you're interested, if you need a present for an upcoming wedding or a birthday, let me know. You get a special price. Usually it's quite expensive to have it sent over because, well, they produce it in the Netherlands. For me now, in the UK, it's quite expensive to ask them to send it to me because there are taxes, right? Taxes, I mean, after Brexit, it's, you pay so much more.
Oh,
so
when you do it go fast in France?
I send it directly there. Of course, that's what you should do, right?
Are there not, import issues if you are attempting to take one of these things back? I mean, I'm happy to skip out on duty. I don't really care. But I probably shouldn't say that in. Is this being recorded? No, I was a joke.
Home security.
Well, I brought them all over, just like that, in a bag. So I took a plastic bag. It looks so inconspicuous that no one ever even thought of asking me.
I think this is being. I think you are admitting to.
No, it's my own stuff. And if people happen to like it, okay, I'll give it away for. Is that okay? What?
There's Alexander. Alexander, he still owns it.
No, for Alexander, it's a special prize, and.
I think it's fine. No, I think.
I mean, as long as it's not really commercial.
Yeah. It's okay for two friends to give one another gifts, is it not?
Exactly.
At the same moment.
I guess his OpenSCAD is aimed at CAD, whereas Blender is computer graphics.
That's right. Yes.
Yeah.
Mm. So you really need to get into that.
I don't know. I mean, Gap is easy.
Yes. But could you in Gap produce one of those knots? And then the ones that you showed yesterday, like the trefoil, but in a cubical version.
Oh, I could give you the Thermophilus protein if you want.
But could you possibly get it in a form that we can STLify?
Yeah, I can give it to you as a union of polyhedra, kind of a nice, kind of curved.
Okay, and for those permutohedra, you have the vertices. So you can take the conic hull of
yeah, I have the center of every. It's a tessellation of the.
Maybe it's better to not take the solid ones, because it takes forever to print a solid object. That's why I also went to wireframes. So each one of those permutohedra could be a wireframe.
It's finished. Very small.
Very small. Okay, could you have a larger version? Will take much longer, right? But
yeah, I double the size.
Okay, great. Thank you.
In France, 12:30 and lunch is.
Okay.
It's just in case
no, I think he Did you have lunch already?
Yeah.
Okay, great. So we don't have to worry about you going hungry. Oh, what's that on the left? Oh, danger.
What? No, it's okay.
Yes, I know. But you don't have any rims or?
What?
So there are things that you put around the model. Typically, the slicer does it.
Yeah, it's
a brim.
It's a brim.
Yeah.
A skirt. That's what you're talking about.
Yes. And then, but here it was still so showing what was left over. Something was left over from the previous print, I guess. That's.
When it comes initially.
Yeah, that's the skirt.
But it shouldn't eject that much. It's probably still left over from the previous one.
I think it just carried it over. Typically, it goes somewhere to the edge of the plate. Does a small there.
Yeah.
Just to
And that's why you also want a brim
Yeah.
that makes sure that everything is.
What is it that you're building?
This is a moduli space of genus zero curves with 6 marked points.
Okay, so it's going to be some kind of a polytope.
Polytope, yeah. don't dumb it down. Come on. M06. M06. That's, you've heard about it.
No, not really. No. So you go. I'm gonna see.
Associahedron. You've heard.
Yeah.
Stashev polytope.
Yeah. All
Okay.
That, yeah.
That's a Stashev polytope. The only Stashev polytope in dimension 3.
Oh yeah. Okay.
So it's unique.
Is it the low-day coordinates of it or something?
No, low-day coordinates are integers that don't really matter, make any sense for print. Well, you could print it, of course. You're right.
But it's okay. Yeah.
It's not that pretty.
Yeah.
I mean, it's nice to know that it exists.
Yeah.
And for that reason alone, one should, of course, print it. But if you want it for aesthetical reasons, you take sort of a version.
Yeah, nice.
And I've taken, well, a version where I think you couldn't put faces there because it's not really embeddable as such in R3 as a polytope. I think the angles don't add up to the.
You're taking straight, everything's straight.
Since I take edges, no one sees the faces. So that's. I think that's cheating, but no one really.
But I don't understand now because if your edges are straight, the faces would have to be. Oh,
No, they're
not planar,
five. Yeah, they're not necessarily triangles only.
Yeah.
Yes, they're not planar. Yeah, and you can see how it decides to jump from one to the next. Aluk has responded.
At the bottom is a vertex or a face? I don't understand.
At the bottom is a face, but well, 4 edges, I think, most likely. Yes, so you can see the symmetry. And now it's already producing the next vertex. Okay. So I think that's the faster one. They have an 8mm nozzle. Usually you have 0.2. If you take 8, it's much, like 4 times faster. But it's, of course, much rougher. So it will not be as neat, the printout, but you will have an object in almost no time. That's great.
This is perfect. As we're here, there's a student in Galway who I'm away, and he's working on collapsing the Stashev polytope. So I'll have to show him this video. This is the opposite, isn't it? Exactly. You just play it in reverse.
Well, you just take the slicer program. if you go down in the slicer program, it will just cut off everything that's lacking. That's not.
It's okay, yeah, unfortunately.
Is it like Morse theory?
Yeah, no, but it's not quite Morse theory. It's discrete because when you come to a, you have to make choices. Yeah,
Okay.
Yeah,
Okay.
So it is the combinatoric, but still.
Okay, yeah, it's great. Well, maybe that would inspire you to buy one of the jewelry items of that time. So, anything produced? No? So no one wants the chocolate? Well, then,
Oh, no.
yeah.
You have
one? Yay.
Oh, yeah.
Okay, cool. Is it hollow? So is it hollow? Can you make it without non-solid? So solid objects take a long while.
Like to take
So take something out from inside where you don't really see, like from the bottom, where you don't really look. Take the same object more or less, slightly smaller. That helps a lot with the speed of the print. Other candidates? Or at least, are you having fun with the program? So maybe until tomorrow, why don't you produce something maybe if you have more time or more leisure tonight? You can take two objects from Thingiverse and load them in and take their difference. Maybe something emerges, something interesting. I don't know.
It's hard to see.
What? Well, you see 5 gons. You see 5 gons, right?
I see 5, yeah, I see the 5 gons.
Well, I mean,
Oh, you have one there.
if nothing else, I might still have one on me. Well, it's definitely over there. No, that's a different one.
And so the coordinates you're taking on those are really non-mathematical, they're trinsic coordinates.
Pretty much. So I tried to compute them roughly to a square.
Squares are plain squares.
And then, no, essentially the vertices. I just took the vertices in a way that I take the 3 squares around, I think, the center, equator,
But you can,
in equal.
But you can't, no, it's in 4.
And then all the others are determined, essentially. You just need to give it a top and bottom. That's all I did.
Why are your faces non-planar?
Because there are 5 gons, so you have 5 edges somehow connected together in space. Well, they might or might not form a...
But you can, but you...
I think the angles don't add up to the right thing.
Because every edge is... So what?
Yeah, you need the angle sum having...
there are realizations, but what's the difference between a realization as a polytope and what you're doing?
Square, so... I think you can probably do it without squares. It would be something like a random foreground. Yay!
This is just for hanging on the one on the top is just so you can hang it outside.
Exactly. That's for the Christmas tree. Or, well, it's a... It's supposed to be a pendant, but maybe this is not... Great. Yeah, nice. Okay, that has a nice size. And that's with the 8 millimeter nozzle.
Yeah.
Mm-hmm.
Maybe what is important to say to the people who are not used to the 3D printer, we can do that because it is small. With bigger parts, we have to make support.
Right. Mm-hmm.
And yeah, that's why, I think more than that, it will be harder to print it without support. You can see that the shape of there is really not good because of the printing in the air. But yeah, still it works.
Mm-hmm. But the angles actually are reasonably
Yeah.
large.
Yeah.
So it should be able to print it without too much.
Maybe it's because it's 0.8, so the layers are thicker.
Right.
So
Yes.
there are more heat in each layer.
Yep.
And it's cooling down to not yet fast enough to be stable, I think.
Yes, that's right. That's right. So on a machine with a finer.
0.4 millimeters nozzle, it will be better.
Mm-hmm. Okay, great. So I guess 12:30. So for anyone who has better things to do, like lunch or